So we did a lot in chapter 7. The last thing we have to do are the double angle and the half angle formulas. And I'll show you what those are and we'll do some examples in a second. Remember, the way chapter 7 worked is, we started with inverse functions and equations, and then we did identities and all of these formulas. So these are kind of the last group of formulas we have to cover before we can move on to other applications. There is a section 7.7 which we're not really going to talk about at all. So we're going to skip this. I'll mention that again tomorrow or Wednesday. But 7.7 is another section about formulas that just don't come up all that often to justify me spending an hour on. But we will study 7.6 pretty long. I don't think we'll finish it today. We'll see. Because these formulas do come up again. In fact, a bunch of people failed. Couldn't answer one of my top 2 questions because they couldn't use these formulas. So they're going to come up again if you're going on in math. If not, sorry, I don't know what to tell you. You're stuck listening to what I have to say. So double angle formulas is where we'll start. What double angle formulas are going to do, and we'll verify the cosine 2 theta one in a second, but what double angle formulas are going to do is take cosine or sine of 2 times an angle and give you a formula that gets rid of this 2. So for example, cosine of 2 theta is equal to cos squared theta minus sine squared theta. And sine of 2 theta is equal to 2 sine theta cos theta. So what happened is we had 2 theta, we had a 2 times theta inside, and we ended up with just a 1 times theta. Just a single theta. And in each case, we turned the 2 theta into a single theta. That's what double angle formulas are meant to do. They take a double angle and turn it into a single. Let's go ahead and verify this top one here. This is almost like the extra credit I gave you, which some of you got. So that's good. But to verify, so to actually make sure I'm not lying to you, what could you do to turn cos 2 theta into cos squared theta minus sine squared theta? Using this identity, I kind of circled it as a hint. How can I apply this identity to this situation?
Cos theta plus theta.
Yeah. So you want to derive this formula, the trick is to realize that 2 theta is an addition problem. Right? 2 theta is really theta plus theta. So just to start off, to get our foot in the door here, we can derive this first formula by saying cos 2 theta equals cos theta plus theta. Why in the world does that help us? Because we know how to deal with addition inside of a cosine. Right? When you have addition inside of a cosine, here's your formula. So according to the formula above, cos theta plus theta, cos theta plus theta will be equal to cos theta, sine theta. Right? Because the alpha and beta are both this other angle theta. So if I just copy this formula down, what happens here? What's cosine times cosine?
Cos squared.
Sine times sine. Sine. That's what the formula says. So we're getting a null. We're going to get like 8 formulas in this section. Okay. These first ones just come from applying the angle addition formula. All right. All of these formulas will be given to you. I'm not going to make you memorize any of them. All right, so on the final exam you'll have them. But I want you to have a small idea of where they come from, and then we'll try to use them in a couple of examples. Questions? By the way, you guys are really good at graphing tangent. That was the one thing that like almost everybody got right. I don't know why. It blew my mind because most people suck at graphing tangent. So good job on that. Kudos. Tangent graphs. Let's work through some of these examples. So I listed all of the double angle formulas for you here. I wrote 2 of them down, the cos 2 theta, sine 2 theta, tangent 2 theta. I usually just do sine over cosine if I'm going to do tangent, but if you want tangent 2 theta, here it is. And each of these is going to come from using the angle addition formula with theta plus theta instead of alpha plus beta. Okay. So in the not to scale right triangle below, A equals 5 and B equals 2. Find sine theta, cos theta, and then find sine 2 theta, cos 2 theta. So I gave you a right triangle. Said it's not to scale, probably because my side lengths are all jacked up. A is supposed to equal 5 and B is supposed to equal 2. C is the hypotenuse, we don't know it yet. Ask you to find sine theta, cos theta, and then sine 2 theta and cos 2 theta. So how do you find sine theta and cos theta? From a right triangle. SOHCAHTOA, right? We've been doing that since second day of class maybe. So we're going to need this hypotenuse first. What's the hypotenuse? Square root of 29. A squared plus B squared equals C squared. So let's see. 25 plus 4, C equals root 29. Since it's a hypotenuse, we'll use the positive. So then we can find sine and cosine. Sine theta would be equal to opposite over hypotenuse, which is 5 over root 29. Which I'm not going to rationalize because, I don't know, I'm just a rebel today. Cos theta is adjacent over hypotenuse, which equals 2 over root 29. This is great. This is fine. We've been doing this. We know how to do this. I hope. Right. So the question is, how do I use this now to find sine of 2 theta, cos of 2 theta? So you could do sine of 2 theta equals sine theta plus theta, and cos of 2 theta equals cos theta plus theta. But let's go ahead and instead use the nice formula we just wrote out. If you want to know sine of 2 theta, you take 2 times sine theta cos theta. And if you want to know cos 2 theta, you take cos squared theta minus sine squared. So in order to do sine 2 theta, what do I plug in here? 5 over root 29, and here 2 over root 29. Right? I know what both of these are now. And knowing what both of these are allows me to figure out what sine of 2 theta is. I'll use right back here. So I just put 2 times 5 over root 29 times 2 over root 29. Which is what?
20 over 21.
So 2 times 5 times 2 is on top, 20. Root 29 times root 29 is on bottom. 20 over 20. I can do the same thing to find cos of 2 theta. I take cos squared theta minus sine squared theta. So I put 2 over 29, 2 over root 29, and square it, minus 5 over root 29. And square it. So you just plug it in. If you know sine theta and cos theta, you can figure out sine 2 theta, cos 2 theta. Plug it right in there. How does it simplify? This is what? Oh, this is unknown. No one has ever discovered what 2 over root 29 is, squared is. All right, well, let's figure it out. So you got to do 2 times 2. You got to square the top, which is 4. And then you got to square the bottom. So 4 29s. And then you got to do the same thing here. Square the top, square the bottom. They happen to have a common denominator, which is nice, so we can subtract them quickly. Negative 21 over 29. Now, does this surprise you that this is negative? I mean, because we started with a right triangle, and everything in the right triangle is positive, so how did this come out negative? Because of the formula. Okay, that's surface level understanding. That's a start. So in order to, what does this formula mean? It's giving me cosine of a double angle. So if I were going to kind of draw a schematic of what's going on here, I would have to double this angle and then do cosine. What this is telling me, though, is when I double the angle, cosine ends up negative. Which quadrant is cosine negative in? 2 and 3. 2 and 3. But sine stays positive. Which quadrant is sine positive in? 1 and 2. So when I double this angle, whatever it is, I don't know what it is, but when I double it, right, here's theta, 2 theta must end up over here. 2 theta must end up somewhere in the second quadrant because it has cosine negative, right? Cosine is adjacent over hypotenuse, and the sine is opposite. So what cosine of 2 theta being negative tells me is that doubling my angle put me in a different quadrant. Okay, I'm going to ask you another kind of thinking question. Kind of brace yourselves. What if I wanted sine of 4 theta? This guy is crazy.
Did we break it out more than once?
So, this double angle formula allows you to change 2 times an angle into the single angle. But here I don't have 2 times theta, I have 4 times theta. So can you think of 4 times theta as 2 times 2 theta? Does that make sense? So I have another double angle here. Double 2 theta. Right, so think of this first 2 as meaning it's a double, but this is what you're doubling.
So it's double double.
Double. Which means if I'm going to break this down using my formula, what should I put over here? Because the formula says, this is the formula, but let me help you a little bit. Let me help you a little bit without using thetas. The formula says if I take sine of 2 times an angle, call it x, then I should get 2 sine x cos x. But I don't want to use x anymore, I want to use 2 theta. So the formula also says that sine of 2 times 2 theta equals 2 sine 2 theta cos 2 theta. So here's a formula for sine 4 theta. This is a formula we can use to get sine of 4 theta. To see if you understand this pattern, let me ask you, what would you write for sine of 26 theta? If you want to break it down using the double angle formula. 2 sine 13 theta cos 13 theta. Why? That's the pattern, right? To get rid of the double, to get rid of a 2 factor in front, you have to cut this 2x in half and turn it into x. So if you have 4 here, then it's a 2 and a 2. If you have 26 here, then it's a 13 and a 13. You always cut this in half. So then what would cos of, I don't know, 22 theta equal? Change it to cosine. Oh my god. This guy is messing with us. This is the formula for cos 2 theta, right? A cos squared minus a sine squared. But my question is, what am I going to put in for the angle?
11 theta.
11 theta. You got to cut it in half. That's the way the formula works. So cos 22 theta is cos squared 11 theta minus sine squared 11 theta. So even though the formula is usually written with 2 theta, it can be applied to any even number theta. So sine 4 theta is double 2 theta, so it's just 2 sine 2 theta cos 2 theta. Yes, miss?
Would it ever work with the odd number?
Yeah, you can do an odd number, but it's going to be a little messier. I mean, I don't know if it's going to be very useful, because if you take like sine of 3 theta, that would equal 2 sine 3 halves theta cos 3 halves theta. And I mean, if you happen to know what sine of 3 halves theta is, this is useful, but you usually don't. Right, the only reason this is useful to me is because I now know I have this information. I know what sine of 2 theta is for this problem, and I know what cos of 2 theta is, because I calculated it. So sine of 4 theta would equal 2 times sine of 2 theta, which is 20 over 29, times cosine of 2 theta, which is negative 21. Whatever that means. cos of 4 theta be here? Yeah, so the formula for cos of 4 theta, the formula for cosine of a double angle is usually cosine squared theta minus sine squared theta. But I don't have 2 theta, so this isn't going to work. I have 4 theta, which means these get doubled. And now I can plug in what I know. Cosine of 2 theta I found right here. And sine of 2 theta I found right here. And you can ask your calculator what that is. It will tell you. Okay? Questions before I move on? All right. Feeling good about the double angle formula. Good, good. So we do another example using the double angle formula. So I give you sine of theta equals negative 2/3. And then I give you some information about theta. I'm going to tell you that pi is less than theta is less than 3 pi over 2. Say find sine 2 theta, cos 2 theta, tan 2 theta. And I know what sine of original theta is, sine of 1 theta. But I want sine 2 theta, cos 2 theta, tan 2 theta. What do you think?
Draw a picture in quadrant 3.
Yeah, draw a triangle first. I mean, if we're trying to get sine 2 theta, the only thing we know about sine of 2 theta in the whole wide world is that it equals 2 sine theta cos theta. So I know sine theta because it was given to me in the problem. I don't know cos theta, but since I have sine theta and a quadrant, I can draw a triangle and get cos theta. So to get the missing information here, you say, okay, well, I must be in quadrant. What quadrant is this? 3, right? Because pi is over here. And 3 pi over 2 is down here. So I know theta is somewhere in quadrant 3. And I can fill out the side lengths of the triangle because I know sine theta is negative 2 over 3. Opposite over hypotenuse. So here's negative 2. Here's 3. What's my adjacent side length? Root 5, right, from the Pythagorean theorem, because you do 9 minus 4. Is it going to be positive or negative? Negative, because you're in the third quadrant. So from this picture, I can deduce cosine theta. Cosine of theta is negative root 5 adjacent over hypotenuse. So then I know this guy. So I can find sine 2. Sine 2 theta is just 2 sine theta cos theta. So you plug it in at this point. And then you multiply it out. Negative 4 root 5. Right, this guy's on top. You think of this guy as a 2 over 1. So then 2 times 2 times root 5. So it'll be positive, actually, 4 root 5 over 9. What do you think? Zombies? Questions? Good. So then you know what cos 2 theta is. Mumble, mumble, mumble. How do I find cosine of 2 theta? Right, start with the formula first. The only thing you know about this is the formula. So you write cos squared theta minus sine squared theta. And then plug in what you know to the formula. Cosine, I figured out, was negative root 5 over 3. But the formula has a square, so I square it. Sine, I was given. Work it all out. Root 5 over 3 squared, 5/9, right? When you square root 5, you get 5. When you square 3, you get 9. Minus 4/9. So cos 2 theta is 1/9. Cool. Cool. And then what about tan 2 theta? Right, so there is absolutely a formula for tangent 2 theta in terms of tangent theta. And you can use it, and it will not be wrong if you use it correctly. But since I already have sine and cosine, a little faster route to do tan 2 theta would be sine 2 theta over cos 2 theta. Right, because tangent is forever and always sine over cosine. So 4 root 5 over 9 from part A divided by 1/9 from part B. So when you flip it up, 4 root 5 over 9 times 9 over 1. Tangent of 2 theta is 4 root 5. Massively exciting stuff. How do we feel? Yes, question.
So we would have to use all 3 formulas for each problem? So
Say again now?
we'd have to use cosine.
Depending on what it asks for. If it asks for all 3, sine 2 theta, tan 2 theta, cos 2 theta, if it asks for all 3, yeah, you're going to have to use
Oh,
that.
okay.
If it only asks for one of them, then you just use that one. Okay. So to get to the half angle formulas, which is what our next goal is, we kind of have to mess around with the double angle formulas a little bit. So I gave you an identity to verify here. Keep you on your toes. So I want you to convince me or somehow show me that cosine of 2 theta is 2 cos squared theta minus 1. How can you prove this or verify this? You know what, you start with cos 2 theta because you have a formula for that. I pick a side to start on, I would start with cos 2 theta because I have a formula. Cos 2 theta turns instantly by the double angle formula into cos squared theta minus sine squared theta. But oh no, this is not what I want, right? I want 2 cos squared theta minus 1. So comparing what I have to what I want, I'd like to keep my cos squared, but get rid of my sine squared. So how do you get rid of a sine squared? The Pythagorean identity. You know that sine squared is 1 minus cos squared. That's his alias. Since cos squared theta plus sine squared theta equals 1, if you subtract, right, because we're trying to get rid of sine squared, so if you subtract cos squared, sine squared theta is equal to 1 minus cos squared. This is just law, fact. So over here for sine theta, I'm going to replace it with 1 minus cos squared. Now be careful, since you're replacing the entire quantity sine squared with the entire quantity 1 minus cos squared, you want parentheses. The whole sine squared was negative, so this whole expression should be negative. And then when you do your small amount of algebra here, you distribute out that negative and you see that you have a cos squared plus a cos squared, which is 2 cosine, which is exactly where we wanted to be. Check, it's a miracle. Proof that God exists. So there's another, this is kind of another form of the double angle formula for cosine. The advantage of this one might be that it only uses cosine. Right? You go from cos 2 theta to 2 cos squared theta minus 1, so you never have to get a sine theta. So it's a little cleaner in some sense. So there's actually 3 different forms of the cosine double angle formula right here. I'm going to use these in a second on the right. So this was the original, cosine squared minus sine squared. Then we just derived the other one, 2 cos squared theta minus 1. The last identity that's equivalent is what you get if instead of replacing sine squared with 1 minus cos squared, if you come back up to this step and you replace cos squared with 1 minus sine squared. Then you get that last bit. So there's kind of a law, a rule, or I guess a law. If you want to get rid of a double angle, if you want to get rid of a 2 inside of a cosine, you have to replace it with a square power. And if you want to get rid of a square power, you can do it by putting a 2 inside of the cosine. So this 2, this double angle, actually translates in a funny way to a power square. This leads us to what we call the power-reducing formulas. You can basically use these formulas backward, and they will allow you to reduce the powers on sine and cosine. They will allow you to get rid of the square on a cosine and change it into a double angle. So cosine squared of theta and sine squared of theta both have nifty little formulas called the power-reducing formulas. So if you come over here and you know, since this is an identity, since this is established, it's true for all theta, you can start manipulating it and move the 1 over to the other side and divide by 2. You get this. And if you take this guy and you subtract, or I guess you would subtract the 1 and then divide by negative 2, it ends up giving you this.
Do we have to memorize this too?
Do you have to memorize them? No, none of the formulas in this section you'll have to memorize. But you will have to know when to use them, right, and how to use them. But no, you will not have to memorize. I will give them to you. Tangent has a power-reducing formula, but no, I don't care about it that much. So these formulas are basically what happens if you solve for cosine squared or sine squared. And what they allow you to do is take a square and replace it with a double angle. So to kind of test and see if you really understand this, what would then, if I wanted to figure out what cosine squared of 5 theta, if I wanted a formula for cosine squared of 5 theta instead of just cosine squared of theta, what do you think will happen?
Replace the 2 theta with 10 theta.
Yeah, so the way these work is to get rid of a square, you double whatever was inside. Right? This square goes away, and this gets doubled. So in order to get rid of this square, you're going to have to double whatever's inside. So this will be 1/2, right? Copy the formula down. 1 plus cos, but then instead of writing 2 theta, which is double theta, you have to double 5 theta. So you write 10 theta. So similar kind of question here. What if I wanted sine squared of 1/2 theta? How does this apply?
Would it just be cosine theta?
Yeah, so you copy the formula down for sine squared that we have here, the power-reducing formula. 1/2, 1 minus cosine, but then you have to double what you started with. Since I started with 1/2, I have to double it. So I'll do 2 times 1/2 theta, which is a single theta. You always double this. So power reducing formulas come in handy later if you keep going on in math. These are the formulas that my students in Calc 2 had a hard time using. And they had to use it actually on a problem like this, just they had to go further. But they had to start with this. So let me take you through this example. I want to rewrite cos squared theta sine, or 4 cos squared theta sine squared theta. But I want to write it using trig functions with powers 1 or less, so 1 or 0. So as a sum of trig functions, with powers 1 or less. See, right now I have a product of trig functions, and that product has powers of 2. So I want to expand, basically this is expanding out the expression. And because I'm trying to change a power of 2 into a power of 1, what formula do you think I'm going to use? Power reducing formulas, right? I'm trying to reduce my power. I'm trying to change a square into a 1. I'm trying to get the power smaller. So I would use power reducing. So to expand this, to rewrite this, whatever, the 4 is the 4. The 4 stays right here. But I can rewrite, I can replace cosine squared with 1/2 1 plus cos 2 theta. That's what my formula is. And I can replace sine squared with 1/2 1 minus cos 2 theta. So to rewrite this, to get rid of those powers, I'm going to replace cos squared theta with 1/2 1 plus cos 2 theta. And then I'm going to also replace sine squared with 1/2 1 minus cos 2.
That's the answer.
All done. Answer the question. Move on. What do you think? Did I answer it? Not quite, because it's not a sum of trig functions yet. And it's actually not powers less than 2, right? It's not powers of 1 or 0. So I kind of want to multiply this out and see what happens to get my sum of trig functions. So I would expand this. First of all, though, this, this, and this can all be multiplied in the front. They're all constants. And multiplication is associative, so you can multiply these 3 before you multiply these 2, right? You can multiply it in any order, change your parentheses. So I'm going to rewrite this as 4 times 1/2 times 1/2, and then leave my other garbage. What is this equal? 1, right? 4 times 1/2 is 2, times 1/2 again is 1. So really I just have 1 out. All right, but I don't care about 4 times 1/2 times 1/2. That's just kind of a tedious thing I have to do. I really care about what happens when I multiply out these trig functions. So what's going to happen when you FOIL here? Difference of squares. Okay, what? What? Difference of squares?
I'm going to get a power of 2 again.
You're going to get a square. Right? Oh, that's annoying. That's okay. Right, but you can multiply this out. The middles the middle is going to cancel, but you have to do 1 times 1 in cos 2 theta times negative cos 2 theta. Right? These guys are going to cancel. You do the inside and the outside. Because this will give you positive cos 2 theta, this will give you negative cos 2 theta, they're going to cancel. So when you do 1 times 1, you get 1. And when you do cos 2 theta times negative cos 2 theta, you get minus cos squared 2 theta. I'm trying to rewrite this as a sum of trig functions with powers 1 or 0, and I just ended up with a trig function squared. So what do? Give up, throw in the towel? I'm done. It sucks. That's this problem. Yeah, okay. I don't. I keep beating my head up against the wall. How do I get rid of a square? Power. So it's kind of like this situation where I cos squared 5 theta and I could rewrite it with cos 10 theta. Well, now I have cos squared 2 theta. So cos squared 2 theta can be replaced with what? 1/2, 1 plus what? Cos 4 theta. The trade-off is, whatever you start with, you have to double. Right? If you start with 5 theta, you end up with a 10 theta. If you start with 2 theta, you end up with a 4 theta when you apply your power reducing. And so we've traded this power for more on the angle, for a larger angle. So altogether here I have, continue over here, I have 1 minus cos squared 2 theta, but I'm going to replace that with 1 minus 1/2, 1 plus cos, sorry, this was 2 theta. It was cos squared 2 theta, so I have to replace that with a 4 theta. I have to double the angle. Distribute out the negative. See, after you reduce your power away, you can clean it up a little bit by distributing out the negative. Now, since I have 1 minus 1/2 minus 1/2, am I going to get 0 altogether? Right? 1 minus 1/2 is 1/2, minus 1/2 is 0. No, why is that garbage? These aren't like terms, right? The 1/2 is attached to the cos 4 theta, so it can't be messed with. These two can be flexed. So 1 minus 1/2 is 1/2. So at the end of the day, this guy is 1/2 minus 1/2 cos 4. It turns out that this is a little easier to work with than this. For example, we could even graph this if we wanted to, right? Because it's just got a vertical shift, and it's got an amplitude, and then it's got a period change. But this guy, we have no idea how to graph. Right? So sometimes these power reducing formulas allow you to get an easier expression along. Okey-dokey. So any questions about the algebra I did there? Any questions about anything so far? I'll give you the last set of formulas. And we'll use them. And we'll be done. these are the half angle formulas. I wrote them with an alpha instead of a theta for convenience. I'll explain that in a second. But the way it works is if you want to do cosine of 1/2 of an angle, it ends up being the positive or negative root of 1 plus cosine of a single angle over 2. And if you want to do sine of a half angle, it ends up being plus or minus 1 minus cos alpha over 2. And there's tangent. Whatever. Tangent is tangent. I'll show you, or I'll explain quickly where these came from, but kind of even more important than that is this plus or minus business here. This should be making you really angry, although I can sense it's not. The sense is making you really bored, if anything, but it's making you really angry. Because cosine's a function. So saying that you're taking cosine of something and getting out 2 different values, that's just garbage. Right? Cosine always should give you 1 single value because it's a function. For each angle, there's exactly 1 y value. So this plus minus, you have to choose either the positive or the negative branch. Right? You choose this sign depending on the quadrant. You have to make the choice manually. Choose depending on the quadrant of 1/2 theta. Or 1/2 alpha, I guess, since I call it alpha. Right, if 1/2 alpha, if half of this angle alpha ends up landing in the 3rd quadrant, then you know sine will be negative because it's in the 3rd quadrant. So you choose a negative. Another kind of quick comment while I'm thinking of it. Sine of 1/2 alpha is equivalent to sine of alpha over 2. So depending on which book you're looking at or which homework exercise you're looking at, you might see 1/2 alpha written as alpha over 2. That's just kind of a notation. So do you guys see where these come from? No? Everything in this section kind of builds off the previous formula. Right, if you remember our power reducing formula said, for example, that we can exchange a square for twice the angle. So all the half angle formula does is it plugs in, instead of theta, plug in 1/2 of alpha, plug in this quantity. So if you rewrite this as cosine squared of 1/2 alpha, what should you get on the other side? So right now, just recopy exactly what you see. I'm just saying I want to put in 1/2 alpha right here. So put in 1/2 alpha right here. The way the power reducing formula works is you exchange the power for twice this angle. So if you double 1/2 alpha, I'm done. Square root both sides to get rid of the square. Then you have this one. So the half angle formula is really just an extension of the special case of the power reducer. But it allows you to take half of an angle and write it in terms of just a single angle, the original angle. Let's do, I'll do one example and then I'll leave the others for next. I don't know not to scale or a triangle. I'm giving you one side length is 15, the other side length is 8. I want you to find sine of 1/2 of this angle and cosine of 1/2 of this angle. So I give you a right triangle. A is 15. B is 8. Right, that's given. C we don't know. And I want to find ultimately sine of 1/2 theta, or theta is this angle here, and cosine of 1/2. So the formula for a half angle, for sine of a half angle, and for cosine of a half angle, they're written right here. I know as soon as I see a half angle, the only thing that I can apply is the formula, right? There's no other tricks to simplify this. So if I apply the formula to this immediately, I get plus or minus square root of what? So apply this formula here. 1 minus cos, in this case it's theta, right? Right? You take this half angle and change it into a full angle. Over 2. This is just this exact form. So if I want to know what sine of 1/2 theta is, I need to do two things. I need to figure out what cos of theta is, and I need to choose a sine. Let's start with the cos theta. How can I find cos theta? Find C, and then you can do adjacent over hypotenuse. So this guy I don't know right now, but I can calculate him in this triangle up here. I know that 8 squared plus 15 squared should equal C squared. So 64, 225, so it'll give me 289. So C equals 17. Which means cosine of theta is equal to adjacent over hypotenuse, 8 over 17. So that's what I plug in here for this entire cosine theta quantity. This whole thing is going to become 8 over 17. Which I don't like because it's ugly, so I'm going to simplify it. 1 minus 8 over 17, well, think of the 1 as 17 over 17. So on top, when you do 1 minus 8 over 17, you're going to get 17 minus 8, which is 9 over 17. then what do you do about that 2 on the bottom?
Multiply.
Flip it up and multiply. Right, this is 2 over 1. You flip it up. It'll be 9 over 17 times 1 over 2. So 9 over 34. And you go straight across. And I know the square root of 9. Square root of 9 is 3. But I have, in my old age, become far too lazy to rationalize. So I'm going to leave it almost like this. You notice I kept writing this pesky plus or minus. But I can't have 2 answers for sine half theta. I just need 1. Is this going to be positive or negative at the end of the day, and why? Positive, because why? So, yeah. See, theta here is acute, right? Theta here is less than 90 degrees, right? Because it's in a right triangle. So if you take an angle that's less than 90 degrees and you cut it in half, it's still less than 90 degrees. It's still in the first quadrant. So basically we have theta. And so if you cut that in half, theta over 2 would still be in the first quadrant. Now you have to be careful because, we'll do this next time, but if theta is in the third quadrant, say, way over here, then when you cut that in half, you're going to end up somewhere up here, and your signs are going to change. Because you change quadrants when you cut it in half in that case. But in this case, because we had something less, because we're in a right triangle, this guy's in the first quadrant, so theta over 2 will be in the first quadrant. So this will be positive. Maybe I'll let you simplify this one, but it should just end up being 1 plus cos theta over 2. Right? The formula for the half angle for cosine is exactly the same except with a plus in the middle instead of a minus. So it'll become plus or minus root 1 plus 8 over 17 over 2. And then will this one be positive or negative? Outside. Positive again because we're in quadrant 1. Quadrant 1. This is not what we have right here. So then you can do your simplification on that. I'll stop on Wednesday. I'll finish up. I have a couple more half angle examples, so we'll go over that some more definitely. And then we'll move on.